Okay, this topic is called terminal velocity. The objectives are to understand what is meant by acceleration due to gravity and also what is meant by terminal velocity. So quickly check on the spec, talking about near the Earth's surface, an object falling freely under gravity has an acceleration of about 9.8 meters per second squared. And then an object falling through a fluid initially accelerates due to the force of gravity, then eventually the resultant force will become zero and it'll move at a terminal velocity. Key you understand the word fluid doesn't just mean liquids. A fluid is something that can flow, so that refers to liquids and gases. So let's have a look. An object near the Earth's surface falls at an acceleration of 9.81 meters per second squared. This is called the acceleration due to gravity, and it will be given in an exam paper, but worth remembering, worth writing that down. If we look at an example, if you drop the ball from the top of the Leaning Tower of Pisa, as apparently Galileo did, how fast would it be travelling after 4 seconds? So using the acceleration equation, 9.81 meters per second squared, this means that the velocity increases by 9.81 meters every second per second. So we'll be travelling at 39.24 meters per second. Galileo tried to prove that falling objects would fall at the same rate, the same acceleration. Obviously not the case if air resistance has an effect. So let's have a look at a skydiver falling through the air. There is air to consider. So at first, the skydiver may fall out of a plane. The only forces on him, an unbalanced force, is his weight acting downwards. So to start the jump, the air resistance is zero. He accelerates at a rate of 9.81 meters per second squared. He falls quite quickly, quite fast, because that is quite a fast acceleration. And after a short time, air resistance will start to have an effect. And this means there will be an opposite force upwards. So the unbalanced force downwards is less now, so he'll accelerate at less of a rate. Eventually, when he's going fast enough, the air resistance will be so big that it will balance the weight of the skydiver. And at this point, the forces are balanced to it, so you measure it as constant speed. This is Newton's first law of motion, you may remember. Forces are balanced. He will continue at a steady velocity, or a terminal velocity. Terminal means he won't get any faster. That is, of course, if he doesn't change the shape of his body. Okay, key that you draw these down, 2 more to be added on the next slide. So he now opens his parachute. What effect does that do? Well, the force downwards is his weight. That is not affected, exactly the same. So the size of that arrow is always the same. However, with a much bigger area, due to the parachute, you get more air resistance, and therefore you've got a bigger force upwards. So he now starts to decelerate. The forces are unbalanced, he will decelerate. And he gets slower and slower and slower until eventually that force upwards gets smaller because he's not traveling at as fast a speed. So he slows down, so the air resistance will balance again the weight. And he now travels at a much lower terminal velocity. So you want to sketch these graphs down, these diagrams down. So the graph, if we graphed his motion, plotted a graph of his motion, he would accelerate very quickly at first, in fact 9.81 meters per second squared, and then that would decelerate until he'd reach a final or terminal velocity. Then the parachute opens and he would decrease his speed and then eventually reach a newer, lower terminal velocity. And then he hits the ground with a thud, and that force, impact on the force, brings his velocity down to zero. Again, he obeys Newton's first law because there would be the force of the ground pushing up would match his weight and he would no longer be moving. What would that look like on the moon? On the moon, there's no air resistance, but also gravity on the moon is much smaller. So on the moon, he would travel like that. The parachute would have no effect. There's no air. So he would just accelerate at a steady rate and just keep on accelerating until he hit the surface of the moon. Okay, you want to write that graph down. Thanks again for listening. Hopefully you now understand the concept of terminal velocity.